Hi there, Mr. Sutton bringing you this lesson on the power rule. For this one, we're going to quickly find derivatives of polynomial functions with the power rule and derivatives of functions that have rational and radical terms. For the real-life application, we're going to use our power rule to find the instantaneous speed of a jet plane.
For the warm-up on this one, let's start by finding the derivative or slope of some functions with which you're very familiar. Pause the video, give it a shot. All right, so in general, you'll recognize these are both equations of lines, and the slope of a line, which means its derivative, is going to be a constant. So for this first one, this is a horizontal line through y equals 7. Horizontal line means we have a slope of 0, so we could say that f prime of x equals 0. Would this have been any different if this had equaled 3 or 5 or pi? Nope. Slope of horizontal line is always 0, so we can define a constant rule for derivatives. We can say d over dx of c, where c is a constant, is always going to equal 0. All right, for this next one, the line 4x, we recognize this in mx plus b form. We have a slope of 4, so we can say f prime of x here just equals 4. And this would have been the same if it were 5x or 7x. We would have just taken the coefficient of x. So in general, we can define a line rule for derivatives. If you take the derivative of something in mx form, you are just getting the coefficient of x, which is going to be m in this case. Now that we've figured out derivatives of linear functions, how do we deal with something that's not linear, like this negative 3x to the 80th? Well, since it's not a line, since it's a curved function, that means that the slope is going to depend on where you are on the function. So when we take the derivative of this thing, we're actually going to get a formula that has an x in it, which lets us pick and choose which x values we're plugging in. In situations like this, when you have a power function, we use something called the power rule. The power rule states that for power functions, we're going to multiply the exponent and coefficient together, and then just decrease the exponent by 1. So in general, just to write the general rule here, if you're taking the derivative of something in ax to the n form, where a and n are both constants, we're going to multiply the exponent and coefficient together, so n times a, and then decrease the exponent by 1. So this is going to be times x to the n minus 1. With this rule in mind, pause the video and see if you can apply it to this problem down here. All right, let's see how that went. So multiplying the exponent and coefficient together, we have negative 3 times 80 is negative 240, and then decreasing the exponent by 1, we write x to the 79th power. And just like that, we've got the derivative of an 80th degree term.
So now that we've gotten the power rule down, we're going to take it for a test drive on something a little bit bigger and faster, namely the Wave Rider, which is an unmanned hypersonic jet launched from a B-52, and it can travel over a mile per second, pretty quick. Now let's suppose that the distance of this Wave Rider in feet, t seconds after being launched, is given by this s of t formula. So 11t to the fourth, 20t cubed minus 4t squared minus 34t plus 2000. Lots of things going on in here. Clearly this is growing very quickly. So we'd like to know a couple of things. First off, we want to find a formula for the jet's velocity, where velocity is just the instantaneous rate of change or derivative of s prime. So we're going to have you try this one out on your own, just as a little bit of a hint while you're doing this. So you actually can, for polynomials, differentiate term by term using whatever derivative rule you want here. So pause the video and give that a shot. All right, so we're going to use the power rule on each of these terms individually. So for the first term, 4 times 11 gives us 44, and then we have t to the 4 minus 3, t cubed. Next up, we've got, this will be negative 8t to the first, actually no, we got to do this one first. So 60t squared, and then negative 8t to the first. And then this will be just negative 34, that's our linear rule. And then derivative of 2000, we don't have to write it, but it is a 0, an invisible plus 0 there. So there is a formula that will tell us the velocity of this thing any number of seconds after the launch time that we want to put in. Here's something else we're going to do now. We're kind of curious what the velocity is at exactly 6 seconds. So we're going to have you do this 2 different ways. In the first way, you're going to take this s prime that you just came up with, make a new name for it, something that doesn't have a prime, and put that in Desmos and then plug 6 into that and see what you get. And then after you do that, you're going to verify that this is actually the correct formula by writing the s of t that we gave you here in Desmos exactly the way it's written here, and then doing s prime of 6 to take the derivative of this at 6. And let's see if we get the same answer. Okay, so for the first part of this, entering our s prime of t in there and putting 6 into that directly, I'm going to call this f of t. I could call it pretty much anything I want, but if I have a prime on it, Desmos is going to misinterpret what I'm trying to do. So let me just give it its own kind of name. And this is going to be 44t to the third plus 60t squared minus 8t minus 34. I don't need the plus 0. Now that I've got that in there, I can plug whatever I want into it. Let me just do f parentheses of 6, and it gives me 11,582, and that's going to be in feet per second. Now another way of doing this would be to enter the original, which is this s of t up here. I am going to call this s of t, and we'll have 11t to the fourth plus 20t cubed minus 4t squared minus 34t plus 2,000. And now I'm going to go down to the next line, and to take the derivative of this at a single x value, I can just use the function name with a prime next to it, like so. And then I'm just going to put what I want to plug in there right next to it. So let's do 6. And now what Desmos has done is it's figured out its own derivative for this, plugged 6 into it, and it gets the same answer that we got using our derivative. So either way, we end up with 11,582 feet per second. And if you're curious exactly what that is in miles per hour, it's roughly 7,900 miles per hour. Pretty quick.
For our next problem, we're going to see how we can deal with some rational and radical functions, like this crazy expression here. Now, you might be wondering what this has to do with polynomials and the power rule. The trick on these, you might recall that these can all be expressed as powers in the numerator. So that's what we're going to do on this one, is rewrite all of these with negative and fractional exponents. And then we can actually use our power rule. Pause the video and take a moment to rewrite these with those kinds of exponents. All right, so going from left to right, this first term we can write as 5x to the negative 8. This next one, we're expressing a radical as a fractional exponent. Remember, it's going to be the power divided by the root. So this is going to be 2x to the 7 over 4 that we're subtracting. And this one, we've got a little bit of everything. This would normally be x to the 1 over 2, invisible 1 and invisible 2. Since it's in the denominator, this is going to be a negative 1 over 2 exponent, because that would give us the reciprocal. So those are our exponents. Pause the video again and see if you can apply the power rule in each of these situations. All right, so going from left to right again, we've got, we're just multiplying exponent times coefficient, decreasing the exponent by 1. So negative 8 times 5, that would be negative 40. And then be careful now, subtracting 1 from negative numbers and also fractions. Remember, it's a little different than subtracting from positive whole numbers. Negative 8 minus 1 would give us negative 9. It should get more negative. For this next one, we've got negative 2 times 7 over 4. That would be negative 14 over 4, or negative 7 halves. And then this would be x to the, well, let's see, we're subtracting 1 from here. So you need a common denominator. We're basically subtracting 4 over 4. So that would be 3/4 for the exponent on x. And now for this last one, this is going to be negative 1/2 times x to the, let's see, this would be negative 3 halves if you subtract 1. For this last example, we're being asked to find the limit as h approaches 0 of all this craziness. Now, you could do this the old-fashioned way and just evaluate this as a regular limit, but this is actually a much faster problem if you recognize that they're really just asking for the derivative of some function. This is just the limit form of the derivative that we learned at the end of the last chapter, Newton's form of the derivative. So in order to do this problem quickly, you just need to figure out which function they're taking the derivative of and what we're plugging into that derivative. So to do this efficiently, we're just going to rewrite the x plus h or constant plus h expression with an x. This 1/2 plus h expression right here, this is really just the x in some general function. So if we wanted to, we could rewrite this as whatever's happening to this 1/2 plus h. What is happening to it? Well, we're raising it to the 8th power, multiplying that by 8, so we can rewrite this as just 8 x to the 8th, and we'll call that f of x. So at this point, all you have to do is find the derivative of this thing and plug in whatever specific value they want you to plug in. Basically find f prime of c. Are we looking to find a general derivative or a specific derivative? If you look back up here, we have a 1/2 plus h rather than an x plus h in here. So they want you to find the derivative of this thing at exactly x equals 1/2. Pause the video and go ahead and do that. All right, so our general derivative here, we've got 64x to the 7th. But now they want us to plug in the value 1/2 here. So we're going to do 64 times 1/2 to the 7th. And let's see here, that's really 64 over 128 if you multiply all that out, which we could reduce if we wanted to 1/2, which is choice B. So this concludes our lesson on this powerful technique. Till next time, Mr. Sutton signing off.